uh, how to get the velocities of fun. Welcome back to the resolution composition. Today I will discuss about how to get the velocities of multiple points in a body which may be a combination of the methods we've used with the previous examples. And also in this lecture, I will demonstrate on how to use resolution and composition in determining the velocities in a 4-bar linkage. But before we proceed the 4-bar linkage, let's first take the last example, this figure below. This is a figure 3-9 in the textbook, page 44 of the textbook. So in figure 3-9, we have a body composed of 4 points where the velocity of point A is completely known as it is represented by this velocity vector VA, while the velocity of B is not, magnitude is not known, but we know the direction and sense of its velocity represented by the line BM. And the velocities of point C and E are completely unknown. Thus, we are tasked to obtain the velocities of the 3 points B, C, and D. Alright, so let's go to the figure. Alright, so let's go to AutoCAD right now, and I'll have to demonstrate on how to obtain the velocities of the 3 points. Okay, so this is our figure right now. So first is since we have to find the velocities of points B and D. Okay, so I think it is in coincidence right now that these lines, these 3 points are collinear. So first is we have to use the method we've used in the previous examples. We have to connect these 3 lines. All right, so right now we're lucky that these 3 points are collinear, so we just have to connect or draw a line in between the 3 points. All right, so next is that we have to extend the line at point A so that we can resolve the velocity vector VA into components. Okay, we'll have to extend this to right here, and now we've got this. All right, so next is we have to draw a line perpendicular to line AB. So this is our line AB. We'll have to draw a line perpendicular to this line. All right. Okay. Okay. So this is perpendicular, right? So next is that we have to, by resolving the velocity vector V into components, we have to transfer this line into the end of the vector. Then we have to extend this into the line AB. Okay, so we may have to chamfer, use the chamfer command to close this to a polygon. All right, so we have to assign these 2 points as A and B respectively. Okay. Alright, so we now have points for the components of velocity vector VA. Okay. Next, what we're gonna do next is that we have to transfer this length of AA, this component AA, into point B. Alright, so just like what we've done with the previous examples. Okay, so this should be the length of our components right here. Okay, so this. Okay, so I might do a viewports here. Again, I will just it's okay. Okay, so the screen. All right. Okay. So what we're gonna do is I will draw a circle where the radius is equal to the length of AA. We just have to simply move this into point B. Alright. So this point, this intersection is now point B. Okay. So what we're gonna do next is that we'll have to draw a line perpendicular to this line, just like what we've done with the velocity vector VA. Okay, this line perpendicular. Okay, so then we have to transfer this to point B and we have to intersect this. Okay, so it now intersects with the line BM. Okay, so we have to remember this line AA is equal to the length of BB. Okay, now this is now a point. We have to assign this intersection as point P5. Okay, it's now point P5. Okay, so because of this, we can now assign this line as vector. So we'll have to draw a letter or a arrowed line here to this, and now we have now obtained the velocity vector for BB. To thus we now have the velocity for point B. Okay, so we have to assign this as point BB. I mean velocity vector BB. Okay, so we just had obtained the velocity vector for point B. Right. So what we're gonna do next? Is to obtain the velocity vector and the velocity of point B. Okay. Just like what we've done with the previous example, just simply have to obtain the get the components of vector the velocity vector for D by projecting a line that is equal to the length of AA or BB. Just like what we've done with the velocity vector VB, we'll do it with point B. Alright, so same with point B, draw a circle, then move it to point B. Okay, so point B. Okay, so this is now the length D. So this point is now D. Small letter D. Okay. So next is that we might first draw a perpendicular line. Same with what we've done with point B. Okay, project a perpendicular line. Okay, so we now know the first component of the velocity vector for D. However, it's still known the vertical component for this velocity vector. So how should we get this this component? So what we're gonna do is to connect a line between point P and point P prime. Okay, so this is now if you remember, this is what we did with the previous example. In order to get the velocity component, the velocity component for the another point that's collinear with the two known points, or the two known velocities collinear with the unknown one. Okay, so we have to assign this as easy dash line. Okay, so now we just obtained. Okay, so we just found the intersection between this line we made that's perpendicular to this line and this line that connected between point P and P prime. So therefore this is now our velocity vector for point B. Okay, so just have to simply connect this to point D, and this is now our velocity vector BD. Alright, so I think this is just the same process we just applied what we've done with the previous example. Okay, so this is now our velocity vector BD. Alright. Okay, so this example, since we already obtained the velocity vectors and also the velocities for point B and D, our next task is to get the velocity vectors and velocity of point C. However, it is still unknown how we may obtain this velocity. So at this point, we will go back to the method that we've just used in the part 1 of this lecture. So if you remember, in this part 1 of our lecture, we did find the velocity of an unknown. For example, in the it is in the figure 3-5. So if you remember, in the figure 3-5, there was a point. It was a point C that is not collinear with the points A and B. So the point A was known, and after that, by doing or making a similar triangle with B and A, we obtained the velocity of point B. And after that, we did a method, and we obtained the velocity of point C. So, however, in that example, in figure 3-5, the axis Q was known. It was already given the location of the point Q, or the axis Q. Okay, so for this demonstration, we'll have to locate first the point Q. Okay, so this point Q for this example is imaginary, but it is required so that we'll be able to obtain the velocity of point C. Okay, so we have to obtain the point Q. How are we gonna do that? So how are we gonna obtain this point Q, this point small q? Okay, so just simply have to extend this point, the lines connecting between P and P prime. So you have to extend this until it intersects with the line AB. Okay, extend, then extend. So now we now obtain the line Q. So for this we can already assign this point as point Q. Okay, alright, so we now have point Q. Now, in order to obtain another point here, so our target here is we should get this point Q, the axis, that imaginary axis point, capital Q, so that we can project the components, and eventually obtaining the velocity of point C. So what we're gonna do is we have to draw a line parallel to this line AB to point P. Okay, so in doing so, we have to copy this line to this to point P, and now this line is parallel to this line AB. So we have to draw this another line. We now have a parallelogram for that. Okay, so we will form a parallelogram. Okay, so if you observe what we've just done, we resolve this component, resolve those the vector VA into components by drawing a parallelogram. Okay, we can obtain the imaginary axis Q. Okay, how are we gonna do that? We'll just have to copy or draw a line parallel to this line PQ. Okay, so what we're gonna do is, so since it should be parallel with line PQ, we'll have to draw this line from this line to here. Okay, so these two lines are parallel to each other. Okay, so these two lines are parallel to each other. Thus, we'll have to assign this line as this point as point A1. Sorry, so this is now A1. Okay, so this is now our point A1. Okay. Due to that, we cannot project the corresponding components of the lines of the velocity vectors D and B. So we can project it by doing these parallel lines. Right. Okay, so this is now, so we just formed corresponding parallelograms after projecting those parallel lines. Okay. Right. So after that, we just obtained the intersection by projecting those parallel lines, and now we will now assign that point as point capital Q. All right. So this is now a large Q. All right. Okay. So you must say that since all these points are now in the same line with A, B, and A, and it has corresponding points as projected here as small q. So these lines, so this q, this point small q, or even the line capital Q is a component. Is a component of the velocity of point Q. So by projecting this, we need to prove that what we just did by projecting these two lines will prove that this length of QQ is the same with the length of BB, right? So this should be since by following the method of resolution and composition, and they are in the same line, the length of AA, BB, DD should be equal to the length of QQ. Thus, it should follow this. Okay, so we have to prove that. Okay, so we have to prove that by drawing a circle. by drawing a circle with the radius QQ. Okay, so we have to project that if this radius of the circle QQ is the same with BB, BD, and A respectively. Okay, we have to check this. So one of the ways to check this is to move the circle here in BB. Alright, so it coincides. How about with BD? Alright, okay. Okay, so we've just proved that by doing the projection of two parallel lines here, we just proved that the resulting distance between these 2 points along the line AB is the same with the components of B, D, and A. Alright, so we just obtained by that method, by that procedure, we just obtained the axis Q. Okay, so after that, we can now obtain the velocity of point C. First is that we have to connect a line between C and our axis Q. Okay, next is we have to project a circle. Project a circle with the axis or the center at Q to the point C. Okay, so this I will first move this point B here. All right. So we just found out that it has a component. It has a component here at this particular point. Okay, so just like what we've done with the example in Figure 3-5, the concept that getting the velocity of point C, which is actually located here, is the same as getting the velocity of a point here. If a point here, imagine that this is another point here. The velocity of point C here can be obtained by simply getting the velocity of the corresponding point here. Okay, by drawing a similar triangle with the points A, D, and B. Okay, so what we're gonna do is that we have to obtain the component of velocity C by drawing a line perpendicular to this line AB, connecting line AB. So draw a line perpendicular. So this is now a perpendicular line to this. So have to move this to the intersecting point of intersection. So we just obtained. So we cannot now trim this circle. Okay. So this length is now a component of the velocity vector for point C. Okay, so we'll have to assign these points as E and F respectively. Okay. E, this point here, and this point above is the point F. Okay. So since this line is perpendicular, so we have to project a line perpendicular to line QC. Okay, we have to draw a line perpendicular here. Okay, to project to move it to point C. Okay, so the length of of line EF is next projected to this point. Okay, so C will have to draw a circle here with the radius equal to EF. Okay, do that. We're gonna move that here to here. Okay, so this length is now equal to length EF. Okay, I have to expand this. All right. Okay. Now for us to retain this, EF, the length of EF is equal now to line CC1. Okay, you have to assign this another point in C as C1. Okay, it's now 1. Okay, so this, okay, you have to assign this as point C1. Okay, so this length of line EF here is equal to the length of this line CC1, because we simply just projected this line here to here. All right, so what we're gonna do next is we'll have to project another component. And what is this component? The another component is the length AA or DB, or these components of the points along this line. Okay, gonna do is we can copy that line here to there to this, and its length should be equal to AA. Okay, so we have to assign this as point C. All right, so thus we'll have another line to add in this equation. This is CC. Okay, so the components of the length BB and Q is equal to the component CC. So as a result, we now have two components. Since we now have components, we can now get the resultant of these two components. How are we gonna do this? So we just simply obtain the resultant by drawing a parallelogram. So we cannot draw a parallelogram out of these two components. So okay, so just have to copy this line here and also this line. Sorry, I think this okay. All right, copy it here. So this length should be here. Okay. We'll have to check if this length of CC is the same with EA. Okay. No. DLI, we'll have to dime linear here. So it's the length 86.52. If we'll check if this is the same with EA. 6 point. Alright. Okay, dime aligned. Okay, so it's wrong. Dime aligned. It should be dime aligned. 84.33. then length. All right, so I think we're gonna do we're gonna repeat this process with projecting the length of AE. Okay. Okay, copy this to here. Okay, we'll check. $84.33. All right, so we just obtained that the length of AA is equal to CC. Okay, so let's go back and we can now get the resultant by doing the parallelogram. Okay, so this is small c. All right. Okay. Parallelogram. Okay, so this is now our component. Okay, let's first extend this. Alright. Let's copy this line. So this should form a parallelogram with this. Alright, so just form the parallelogram of this. So what we're gonna do next, since these are all components, we have to connect. To connect this diagonal. So since the direction of the velocity vectors, the vectors for A, B, and D are going to the left. Therefore, the direction and sense of the velocity of point C should be the same with the sense and the direction of the 3 points A, D, and B. Thus, we'll have to draw either here or a arrowed line from these to this. So, and thus we obtain this velocity vector. Okay, so we have to finalize this. Okay, all right. Okay, so we just obtained the velocity of B, D, and C respectively, which is a combination of the methods we've used in the previous two examples, or even three examples. All right. So as a summary with what we've just done in this example, the velocity of point A is completely known. Thus, we had the velocity vector of point E represented by VA. The velocity vector of the point B is not known, but we know the direction and sense as we had the line BM. Okay, but the velocity of point C and D were completely unknown. So what we did in getting the velocity vector for point B was we did a projection of the components of velocity vector VA by solving this component into components A, and AP. So we projected that to point B along the line that we have by connecting these lines A and B, and coincidentally it is collinear with point D. And after that, we obtained the intersection of the projected perpendicular line with the direction of velocity BM, and thus we obtained the velocity vector VB. And after that, we obtained the velocity of of point D by projecting the same component AA into the point D. So now, so we already have one component for velocity vector D. However, we lack the second component in order to get the resultant. So how did we get the second component? The second component was obtained by connecting the two heads or the two terminals of the velocity vectors VE and VB. And after connecting that, we have now obtained the intersection of the line perpendicular to the component DD, and thus we obtained the velocity vector for VD. Velocity vector for C involved getting first the axis Q. So at first we didn't know where the axis Q was. So in order to get that, we first extended the line P sub prime until it intersects with the line AB, and thus we obtain the line the point Q, point small q. And after that, we projected a parallel to this line here by forming a parallelogram for the velocity vector VA. And after projecting the parallel line, the intersection of that projected parallel line with the line AB is now the point Q. So this point BQ is now the axis of this body M. Okay, but before doing that, before proceeding with obtaining the velocity of point C, we first check if this length is equal to the components B, BB, TD, and AA. So we further eventually prove that the length of QQ is equal to the length of these components. Thus, this equation. Okay, so this is now. So it should be equal with these components. AA equal AB equals DD. QQ is equal to subsequently CC. And after that, we connected the lines. We connected the line for point Q and C. Okay. So after that, we projected the circle. With center Q to point C, and we found the intersection at the line AB. So after that, we obtained a component by drawing a line perpendicular to AB, and thus we obtained the line EF. So this line EF is further projected into point C, because this line EF is a component for the velocity vector of point C. So thus the length of EF is equal to CC1. This is the length of the length of the components CC1 and the length of the projected EF. And after that, we projected another component. So since they are of the same axis and they are the same body M, we projected the component into point C. So what is the component? The component CC. So this CC is the length of this component CC should be equal the length of these components that we just obtained the other points. Okay, so we have that. So after having two components, we can now get the resultant of these components by drawing a polygon. What is this polygon? A parallelogram. After drawing a parallelogram, you obtain the resultant by connecting the points forming the terminal. And therefore, we obtained the velocity of point C, which is represented by this vector where the direction of sense is the same with the other points in this body. Yeah. All right. So we can now proceed to an example which is informal linkage. All right. So we'll now proceed with our example. So this example is found in the page 46 of the textbook. In the article 3-6, examples of velocities by resolution composition, example 1. So in figure 3-11, we see a 4-bar linkage there, and you have to obtain the velocities by means of resolution and composition method.